Hello friends, welcome to my YouTube channel. Today in this video I am going to discuss two interesting geometric problems. Our first problem is like this. It's called ever-present parallelogram. The midpoints of the sides of an arbitrarily drawn quadrilateral form a parallelogram. So here we have a quadrilateral. In fact, we have two quadrilaterals of different shape, and E, F, G, H are midpoints of the sides DA, AB, BC, CD. So if we join these points E, F, G, H, we will always get a parallelogram. But how do you prove it? Proof is actually based on this theorem, which is like this. The line segment joining the midpoints of any two sides of a triangle is parallel to and is half the length of the third side. So we'll use this theorem to solve the first problem. So our problem is this, that we have to show that EFGH is a parallelogram. So we join DB and apply the above theorem to the triangle DAB, okay, and also to the triangle DBC, okay. Like this we join. So join DB and apply the above theorem to triangle ABD and DBC. What is ABD? ABD is this one and DBC is this one. So here this EF is parallel to DB and its length is half the length of DB. And here also HG is parallel to DB and HG is half the length of DB. So therefore HG and EF are equal, and since both of them are parallel to DB, they are also parallel, and that completes the proof. That's it. So in ABD, EF parallel to DB and EF is equal to half DB. Also in triangle DBC, HG parallel to DB and HG is equal to half DB. Therefore EF is equal to HG and they are parallel, and therefore EFGH is a parallelogram. Our second problem is like this. We have a figure in which, okay, we have a figure like this, in which ABCD is a parallelogram. It is given. EFGB is also, or BEFG is also a parallelogram, okay. And there is an additional condition that this GFC are collinear. They lie, all these 3 points lie on the same straight line, okay. So that's what is written in the statement. In the following figure, the two parallelograms ABCD and BEFG have the same area, where E is an arbitrarily chosen point on AD and the point GFC are collinear. So these two parallelograms are constructed in such a way, this ABCD and BEFG are such that this E is actually an arbitrarily chosen point on AD and these 3 points GFC are collinear. We have to show that this ABCD and BEFG have same area, even though apparently their shapes are quite different, but their area will be same. So what we do? We again join E and C. So we join E and C, and then we'll look at the triangle. Okay. First of all, we join EC like this, and then we look at the triangle BEC. This triangle is lying between two parallel lines, AD and BC. And the same triangle is also lying between two parallel lines, BE and GC. Okay. Therefore, so we join EC and note that triangle EBC lies between two parallel lines AD and BC, and also between two parallel lines BE and GC. That's what we said here. Okay, this same triangle lies between these parallel lines and these parallel lines. Okay. Therefore, it follows that area of the parallelogram ABCD is equal to BC. BC is one of the sides into its distance from the other side, opposite side. So BC into distance between BC and AD. Okay. So area of this parallelogram is equal to BC into this distance. But this distance is also equal to the altitude of the triangle BEC. If you consider BC as base, then the distance between this line and this line is same as the altitude of this. Therefore, area of this parallelogram is equal to twice the area of the triangle. Okay, because area of the triangle is half base into altitude, but base into altitude is equal to area of this parallelogram. So this parallelogram BC into this, so it is twice the area of EBC. But the same triangle lies also between these two parallel lines, so its area, twice its area, can also be equal to BE, that is the base of this triangle, into distance between BE and GC, that is the altitude of EBC considered now in this fashion. Okay, now BE is the base and this is the altitude. Okay. So BE into distance between this, but this becomes actually equal to the area of the other parallelogram BEFG. Therefore, these two areas are same. That's all in this video. Thanks for watching.